Well, hello
Okay.
everyone. Thanks for coming again to our latest seminar in our Australian Geometric Seminar PDEs and Australian Geometric PDE Seminar series. We've been going through Yang-Mills theory this year. Today we've got quite a treat in that we've got an esteemed veteran of the field, Peter Price, who's speaking with us today on vanishing theorems in geometry and physics. And we're quite pleased to have Peter speak with us because he was actually active in doing mathematics at the time when a lot of these results we've been discussing were actually done. And so we're quite pleased to have Peter with us discussing some of his ideas on this particular topic. So take it away, Peter.
Okay, so firstly, a quick outline, simplified outline. So we studied geometrical variational problems, and simplistically, we try to find a nice representative of a topological class by minimizing some action or energy functional. So let me tell you some, get rid of this. Sorry. Okay, I should have fixed that. So examples are energy of is a simple example you might all well know very well. Energy or action of a member of a de Rham cohomology class. The action is just or energy is just the L2 norm of a cohomology class. So basically, phi is the closed form in the de Rham cohomology class C. C lives in HK de Rham of our manifold M. HK de Rham is, we know to be the kernel of D, which is the exterior derivative on forms over the quotient by the image of D. And we'd like to find a nice representative in that cohomology class. It's very easy. We're going to have a set up a one parameter variation of what we putative answer phi, which is this minimizer of this action over this cohomology class, one parameter variation of phi, which we'll call phi t for t in the n minus epsilon epsilon. We want to differentiate to phi sub t. We want to differentiate respect to t and set the derivative of the action to be 0 at the minimizer or stationary point. And as you can see immediately, e by dt of t equals 0 of this energy e by dt of norm phi sub t squared is going to be, I use angle brackets for the L2 inner product and round brackets for the pointwise inner product on the manifold. And this is the twice integral of the derivative of the phi's. So phi, I'll put a dot on the superscript dot there for the derivative of the phi's. And we know that we're in the cohomology class C, and the tangent, that's an infinite dimensional, it's an affine space, infinite dimensional affine space. And we know the tangent space is the image of D. So we know that the derivative of one of those derivatives with respect to time of that one parameter family must be represented by D or something. So we know this is because the tangent space is the tangent space of the cohomology class C is the image of D. So for every one parameter variation, there must be some alpha for which this equation holds. And if we have an L2 adjoint, and we do, to the exterior derivative, then this L2 inner product is equal to the inner product of the variation, what I'll call the variation vector field, alpha, and the adjoint, L2 adjoint of D. And so this must be, we want this to be stationary, so this must be 0 for all alpha in P-1 forms. And hence, the first variation or Lagrange equation is that this delta of phi equals 0, identically 0. And delta is the L2 adjoint. And so this is the order Lagrange equation. And there's not much difference. There's either the same or little difference between that and the first variation formula. Can everyone hear me?
I can still hear you, Peter.
Okay, please tell me if you can't hear me or I'm unclear or if my writing is just too bad to be readable, if possible. And so we do have an L2 adjoint to D, which is delta, which is turns out to be -1 to the NP plus 1 star D star, where star is the Hodge drill. And it's L2 adjoint, so enough said. So our order Lagrange equation is delta phi equals 0 for a stationary point. We already have, we are given that we live in a cohomology class C, so d phi equals 0. So this means that Laplacian phi equals 0, well, Laplacian operators, it's the so-called Hodge Laplacian, which is d delta plus delta d. I just lost everything. Can you?
Everything okay, Peter?
I've gone. Yeah, I've got to try and get rid of this thing coming in at the background.
Anything you
I'm
need help
trying to.
with?
I'll get rid of this in a moment, I hope. Oh. Ah, ah. Right. Well, I don't know why that happened, but I think I bumped the bottom of the screen with my wrist. You still there?
Yep, still there. And we still see your whiteboard.
Okay. Well, that happened once before, about a week ago, and I managed to get rid of it quite quickly. But this time there seemed to be no buttons to get rid of it. Okay. So we have have all Lagrange is delta phi equals 0. and we already knew that d phi was 0, so we've got Laplacian phi equals 0. So that's the first variation. Okay, that was my first example. Here's my second example of variational problem. It works like this. So we'll have the energy of phis being the L2 norm of d phi, where phi is a map between Riemannian manifolds. And so before phi was a form, or the p form, phi was, here's my notation, epsilon superscript p then. That's a p form. And I'm going to be talking a lot about section valued p forms. So if phi is a map between Riemannian manifolds from M to N, then d phi belongs to, is a section valued one form. It's a one form on M with values in the vector bundle, the pullback of the tangent bundle of M. Okay, so one form is an M tensored with tangent vectors on M, which tangent space you're at is given by the pullback of phi. Okay, and once again we find when we do first variation, we get Euler Lagrange equation delta of d phi equals 0. Now there's some debate about whether I should emphasize that I need a covariant derivative for this delta. So I'll add it on, but it's the only extension of the simple exterior derivative that you have on forms, ordinary forms. It's the only thing that makes sense is the exterior covariant derivative. And that's why I've put the little delta on top of the little grad on top of the delta to emphasize that there's a covariant derivative involved, covariant derivative on manifold N actually. Anyway, that's the Euler Lagrange equation for this harmonic map problem. So a solution to this is called a harmonic map, which we've spent lots of time on with the Shannon Uhlenbeck paper. Now, you won't be surprised to know that likewise we have this is the exterior covariant derivative. The previous one was the L2 adjoint. You won't be surprised to know that d delta of d phi equals 0. And that's basically because d delta of d phi is actually the pullback of the torsion. So that on N, so that it is purely because the torsion on N vanishes. Okay, am I running off the bottom of the page? Let me know when I run off the bottom of the page.
You're getting close.
Okay, so once again, we have combining the Euler Lagrange equation and what we're given. We have that the Laplacian of the derivative map is 0 for the harmonic map case. Okay, so I'll go on to a new page. Everyone happy with the new page?
Sounds good.
Oh, no, I can't. Now I can't get a new page. I just checked that the pen's not flat, it might be. I'm charging the pen. Oh, let's see if it works now. I can't get a new page at the moment, so I'll just As I said, I was going through this talk with the whiteboard open. I had no such problem. Everything was working fine. Okay. I'm thinking I'm going to have to log in again. I don't see one.
An alternative possibly would be to just erase everything you've done and start again.
Yeah, okay, we'll do that.
If you think that might be quicker than logging back in.
We'll do that this time. And, I can't believe this thing. Everything worked fine. The previous hour going over and apart from forgetting the start time, not noticing the start. I might go to try and get the screen to take up the full page as well. Maybe that will help. Yeah, I can't go full page either. Can you still hear me?
Yes, can still hear you.
Okay. I'm going to close this other window. Hope that doesn't turn me off. Didn't close it either. Okay. Okay, so I'll go on to my next example. I'm going to use the area of a n-dimensional submanifold and of a p-dimensional Riemannian manifold, capital N, and the Euler-Lagrange equation that I like to write is, surprise, surprise, Laplacian of di equals 0, where I is the inclusion map. And if you look at it, you find that the derivative of I is really the identity when you think of it as a section valued in one form on M, section valued one form on the submanifold with values in the tangent bundle of the embedding manifold. And this is if and only if the mean curvature is 0, as everyone else is familiar with. You guys have worked on this a lot. So that's again, I mean, the Euler-Lagrange equation is delta of di equals 0, and you're given d of di equals 0 because the torsion vanishes. Actually, if you feel nervous, we probably should put a covariant derivative here, if it makes you feel happy. And my fourth example is that the action is going to be the action of a connection on a principal bundle, and that the action is going to be the L2 norm of the curvature of the connection. So omega is a connection on some principal bundle over M with group G. And what was I going to say next? So the curvature is a section valued 2 form on M with values in a bundle, and the bundle is bundle which I call add P, which is got standard fiber, the Lie algebra of the group. That's in the bundle. It's twisted by the adjoint action, but it's modeled on the Lie algebra of the group. Right. And stationary points. Oh, the Euler-Lagrange equation. Did I say that? No, the Euler-Lagrange equation is delta grad of omega equals 0. And surprise, surprise, we have d grad of omega equals 0. And that's the Bianchi identity. So once again, we have Laplacian covariant, Hodge Laplacian of the curvature is 0. But this time it's a section valued 2 form, not a section valued 1 form. Okay. So this, I promised to tell you about Bochner-Weizenbach formulae. So the Laplacian, which is d delta plus delta d, here I'll write the formula down. Here it is. It's Laplacian equals grad star grad plus script r, and I can put a covariant derivative in here as well if I feel like it. So here, that's the so-called Hodge Laplacian. Grad star grad is another second order operator. It's called the Bochner or rough Laplacian, and it's given by it's grad star grad. Well, I won't give the details because this is supposed to be a quick summary. Grad star grad is called the Bochner Laplacian. And script R is a 0 order pointwise operator and depends on the geometry. And I give a formula for it. But you can see immediately that if script R, if Laplacian of phi equals 0, so we have something satisfying the Euler-Lagrange equations, and if script R on phi, well, script R is a positive operator, then this is impossible. We just apply phi to this equation. We take the L2 inner product, dotted with phi, and we get grad star grad phi inner product phi plus this L2 is integral of the manifold phi prime. But grad star is the L2 adjoint of grad, so this is exactly grad phi L2 inner product squared plus the integral of the manifold of point y's R5 phi. So if script R is positive, and we're saying the Laplacian of phi is 0, then that's as impossible. Okay, so, and Gromov-Lawson, when they derive the general expression that I'm going to give you shortly, I hope, when they derive this, they say this formula, which is this formula, is responsible for most of the vanishing theorems. In Riemannian geometry. Okay. Okay, let's go and go to a new page. So this technique that we have of deriving, following Gromov-Lawson, the technique that I show of deriving this Bochner-Weizenbott formula works whenever we have a bundle, whenever you have a
You're
bundle.
heading off the edge of my page there, Peter.
Okay, I'll squash it in here and then go to a new page. Works when we have a bundle of, can you see that?
Oh, I see. It's when my toolbar is there.
Okay.
I'm
Yeah.
struggling, but if I move my mouse away from the toolbar, it tends to be okay.
Okay, I'm just saying that the derivation works whenever you have a bundle of modules over the Clifford algebra bundle. Okay, so I'll try and go to a new page. I got a new page. I think maybe it was it's very hard to understand because I couldn't do it with my finger either, but it may be because the electric pencil had gone flat from all the time I'd spent writing before this seminar started when I was supposed to be at the seminar. What a disaster. Anyway, we'll plot on. So bear in mind that I'm pretty well ignoring existence and regularity here. We're talking about what happens in the smooth category. And we know from the Shane-Ellenbeck paper that we've just finished going through that we do not have regularity, full regularity. We only have partial regularity results. Nevertheless, to progress, I talked about the second variation formula. So as you might expect, we want to differentiate the action twice when we're at a critical point and see if that's non-negative. That'd be nice for a minimum or a stable solution. So this is a second variation formula. Useful when, I think it's where I derive it. It's only accurate when phi satisfies the first variation. And typically, this is equal to it's typically some operator which I try and call script S. That's supposed to be a script F. Script S acting on the variation vector field in a product with the variation vector field, and that's the L2 in a product. And this Jacobi operator script S usually has the form script S of phi dot is equal to grad star grad of phi dot minus script Q. And script Q is related. It's not the same as R, but it has similarities to R, to script R. So if script Q is positive, if that's a positive operator, then we get vanishing theorems. If there exists a variation vector field that's parallel. Okay, so if grad phi dot is 0, then this should be script Q of phi dot, of course. If grad phi dot is 0, then grad star grad term is 0, and we just have the negative script Q. And if script Q is positive, that's going to rule out stable solutions where there's a parallel variation vector field. Okay. So I've already said something about the vanishing theorems. I'll say a bit more in this summary. Then you don't need to hang around or come back because I've said everything, but without any details. Ritchie on M is greater than 0. It implies first Betty number 0, as I think we said. It's Brockner-Weizenbach. Curvature operator greater than 0 implies all Betty numbers are 0. This is Brockner-Weizenbach. 3. Scalar curvature greater than 0 implies there are no harmonic spinners, and so the index of the Dirac operator is 0. So the A hat genus is 0. Ritchie, that's Brockner-Weizenbach. Oh, by the way, anyone familiar with Seiberg-Witten? It happened a long time after I stopped doing maths in this area. It happened in the 90s. Seiberg-Witten uses exactly property 3. Scalar curvature positive means there's no solutions to their equation, which is an equation about twisted spinors. So they get invariance vanishing if the scalar curvature is positive, exactly by what we've just been doing. Anyway, my example 4, if Ritchie is positive on our manifold M, and we're doing harmonic maps now, and the sectional curvatures are non-positive on N, then we have that any harmonic map is constant. That's Brockner-Weizenbach again. If N is even dimension complete oriented compact, and the sectional curvatures N, which are positive, remain in manifold, then N is simply connected. I've got a free ellipse at the bottom, which I can't rub out. Oh, yes, I can. Good. Then N is simply connected. That's second variation. Show there must be a minimizing, length minimizing geodesic in any path class. And then you show that the assumptions mean that it can't be stable, such a thing. It's the second variation, so it can't be stable. Can you still hear me?
Yes,
Okay.
getting towards the bottom of your board there.
Okay, I'll go up to the top because I want to write two of these at the same time. So I'm up to number 6, which is James Simon's theorem. For n greater than 4, there does not exist stable Yang-Mills field on the sphere. Now, the main reason I like this stuff and thought you might be interested in seeing it as well is a great similarity between the results you get on these different geometric variational problems and the great similarity of the techniques. So let me write down number 7, which is Zin's theorem, which is for n greater than 2, there does not exist a stable harmonic map, which starts on Sn, and the target manifold is any n at all. So you can see that those Simon's and Zin's theorem look very similar in flavor. Example 8. Bourguignon-Lawson, and I think I mentioned this before, didn't I? And I think Simon's. Did I just mention this in the overview? Oh, no, this is the overview, so I shouldn't have. Bourguignon-Lawson says any stable Yang-Mills field on S4 with the groups G equals SU2. I think I did say, I have a feeling I said this anyway. With small groups is plus or minus self-dual. And number 9 is Xu and Yao as a key lemma in their proof of the Frankel conjecture. Prove that any stable harmonic map from S2 to N, where N is scalar and has positive, N also has positive bisectional curvature. Is plus or minus self-dual or holomorphic is what it's called here. Okay. And so for some reason I thought I'd already said this, but anyway, I also proved this theorem. But it turned out I'd already proved it, so I didn't think of publishing it. But Xu and Yao used second variation on minimizing submanifold, looking like S2, I think. Whereas I used, if you want to be unfriendly, you'd say I copied the Bourguignon-Lawson technique. I copied their proof. If you want to be a bit more generous, you'd say I modified the Bourguignon-Lawson proof for Yang-Mills on S4 and used analogous steps to prove this result for harmonic maps from S2 into N. Okay, but anyway, it's possible to prove the Xu-Yao theorem by this technique that is very close analog to Bourguignon-Lawson's proof. Okay. I've got myself confused, but I'll go on to I think on the next page and next part of the talk. So I started very late and been going for 40 minutes. I don't know when you want me to stop.
I wouldn't mind if, or how much more would you want to do? I wouldn't mind if you went for another 10 minutes or so, 15.
Yeah, I'd be happy getting that hour, but that's okay. I won't if you want me to stop. We'll see how
Oh,
we.
you can take the full hour if you want.
Okay, let's start 20 minutes probably. Okay. Right. So let me go to it. Try and go to a new page. Right. And I'll do I'm on page 5 of the handwritten notes, by the way. So I'll derive the Weizenbach formula a la Gromov-Lawson. Gromov-Lawson. 1980. And so you can write the exterior derivative on forms as theta I wedge grad I grades the Riemannian covariant derivative. EI, this is Einstein's summation convention. EI from 1 to n is a local frame field on M, of course. And the theta I are the local dual or the dual local coframe field. And similarly, I can write its L2 adjoint delta as the sum minus EI into grad EI on forms. But here the EI, as you know about from raising and lowering indices, the EI must be orthonormal. And I can define dot mapping vectors and P forms. Did I define this before? I sort of got the feeling I've gone through this a bit not long ago. I've got a strong feeling that I've done this before. So this maps into P plus 1 forms and P minus 1 forms. And it's defined X is a vector, phi is a P form. The definition X tilde wedge phi minus X into phi. And tilde is the metric isomorphism. And when you look at this anti-commutator, X dot Y dot action forms, this is the anti-commutator, is the X dot Y dot plus Y dot X dot. That is minus 2 X inner product Y for vector fields X and Y. And this is because the anti-commutator of, say, theta J wedge and EI interior product is actually delta IJ, which physicists would call the theta I wedges creation operators and the EI interiors annihilation operators. And let's say this is the anti-commutation relations for fermionic creation and annihilation operators. Anyway, this is a defining that dot product. This is a defining rule for Clifford algebra. So this makes the bundle of forms a bundle of module modules over the Clifford algebra bundle. So we have a pointwise operation there, of course. And the some good properties of this Clifford multiplication by tangent vectors is that multiplication by a unit vector is orthogonal. And covariant differentiations of derivation. Okay, we can define the Dirac operator. E slash is the sum EI dot grad EI again. This is going to work for spinors as well, of course, but for forms, given this definition of the dot product for forms, we can work out what this means exactly on forms, and it's d plus delta, of course. And we know that d slash squared is the passing. And so I'll now actually work out a different way what d slash squared is. So Laplacian equals d slash squared, but that's EI dot grad EI acting on the sum EJ dot grad EJ, and that's EI dot EJ dot grad squared EI EJ, where grad squared is a covariant Hessian, and grad squared EI EJ is defined to be grad EI grad EJ minus grad of grad EI EJ. And I compute in an adapted frame where not there, but what I'm computing now, I'm going to want the grad in the EI direction of the EJs to be 0 at the point where I'm going to compute an answer. That's an adapted frame. And so my Laplacian is just taking the case where I is equal to J and the form at the top. It's EI dot EI, which is -1. So it's covariant Hessian, EI, so it's a negative trace of the covariant Hessian. And then I have the terms where in the top equation where I is not equal to J, and these EIs are orthonormal. So they anti-commute. If I is not equal to J, so I get plus a half EI dot EJ dot, and then I get the commutator given the difference of, I get the skew part of the covariant Hessian, which is the curvature tensor. So, right, so RVIEJ can be defined as grad squared EIEJ minus grad squared EJ EI. And so we get this Bochner-Weizenbach formula. Laplacian equals grad star grad plus script R, where grad star grad is minus grad squared EI, and script R is a half EI dot EJ dot R of EIJ. Okay. And grad star is in fact the L2 adjoint of grad. And on forms, on forms, we can work out what the exactly what that EI dot EJ dot and then summed over R means. It turns out to be it's a Riemann curvature tensor EI EJ theta J wedge EI interior, and that's by the first Bianchi identity. Because the theta I wedge, theta J wedge term isn't there in script R on forms, and that's the first Bianchi identity. Gives you that symmetry of the covariant derivative, I think. So did I already? I've mentioned that script R on one forms. Did I work it out in full? Before? RFI is well, RFI phi in a product phi is from the formula R of EI EJ theta J wedge EI interior of phi in a product phi, and that's R EI J theta J, and phi is a one form, so EI into phi is just phi VI, which is the number in a product phi. And so we can expand the last phi into a basis. So we'll have 5 EI, 5 EK, and then we have R of EIJ, theta J, and then theta K. In a product with theta K, how it should be written. And so we have J repeated here, R of EIJ, and then theta J, acting on theta J. That's exactly the Ricci tensor. So this is phi EI, phi EK, Ricci of EI, EK. And that's what we mean by, I guess I wrote it. Can you see that?
I can see that if I don't have my mouse on the screen.
So this is what we mean by Rickwood phi, is that we're just doing the obvious quadratic form thing with the components of phi over the Ricci tensor. So, okay, did I do that before? Probably not.
I can't recall.
Okay. Sorry?
I'm not sure.
Yeah. Next page. Okay. I can't get a new page.
If you're struggling, I think I've worked out how to help you out with the erasing if you want to do that.
You can erase at the same time, you mean, or you can erase the
I
whole thing.
think I have the ability to erase your work. Do I? No, maybe I don't. Oh
All right.
no, don't think I do.
Okay. I don't know why. So everything looks the same. I've got the pen flashing up the whole time. Um,
You able to finish within 5 minutes, Peter?
hold on. Yeah, I'll stop then.
Cool, thank you.
The place to stop. Thanks for letting me go on an hour after that markup at the beginning. It's very frustrating. Haven't had this problem of not being able to erase, not being able to get a new page ever before. And I thought it was a flat electric pencil, but it doesn't appear to be. Should be fully charged now. Okay, so script R on P forms, Gallo Mayer did the following computation. You can regard rho as a symmetric two-form valued two-form matrix, and makes sense to say whether it's given by rho of theta I wedge theta j inner product theta k wedge theta l is defined to be the Riemann curvature tensor R I J L K. Notice the reversal of the order of K and L compared to the usual way of doing a Riemann curvature tensor components. And now we can have rows of symmetric matrix. It's curvature operator, we say. We can say makes sense to ask if rho is positive. And if rho is positive, in fact, if rho is greater than k, some number k, then script R of a P form phi inner product with that P form is greater than or equal to k P n minus P norm phi squared. Okay. So that enables us to say if the curvature operator is positive, then on a manifold, then the manifold's a real homologous shear. Or the Betty numbers vanish. I did say that before. Bochner writes and what for spinners. Everything works. What we've been doing, because as I said, works whenever we have a bundle of modules over the Clifford algebra and a fibermetric on the spinners and a compatible covariant derivative, which, and script R on spinners is equal to a quarter of the scalar curvature times the spinner. So I think we mentioned this vanishing theorem before, Horowitz. Scalar curvature positive implies no harmonic spinners, which meant some genus, A hat genus is equal to 0. So I think that's my 5 minutes is up. So, unless you're happy for me to go on at all, I'll stop now. The next thing I was going to do is write some block for section valued forms, but I'll start with next week. And then for section valued spinners, and much of the same, similar things, but with extra terms, which you want to work out what they are. And then details about what you can do with harmonic maps. Working out, well, not in detail, the first variation formula, and the block provides some block formula, and the second variation. Yeah, anyways, and second variation for harmonic maps and appropriate vanishing theorems. I was going to do a bit on area, not much, and then Yang-Mills fields. And then I was going to do those vanishing theorems that I outlined in the simple outline of the talk. So I guess I should stop there, Tim.
All right, let's thank Peter for taking us through all of those interesting results.
Thanks very much for letting me carry on for the hour.
No, it was quite enjoyable to see all of these results. Does anyone have any questions for Peter about what he's taken us through today? Maybe I have one question for you, Peter. Do you have a preferred vanishing theorem? Is there one that you've found particularly inspiring or useful to you in the past?
Well, I guess I just liked it because there was such similarity between the statements and the proofs in many cases. And before I gave this talk, by the time I gave this talk in January 82, I was going around telling some of my maths colleagues like Leon Simon that there were these close parallels, and whatever you could do for Yang-Mills, you should be able to do for harmonic maps and vice versa. And we'd barely got back from that meeting when we went through Shane and Lubbock's partial regularity paper that we've just gone through here for harmonic maps. And so I immediately was thinking there should be an analogy. Instead of n-3 regularity, it should be n-5 regularity for Yang-Mills. And we were going through, Leon was leading us through the Shane Ullenbeck paper. Leon was one of the PhD supervisors of Rick Shane. We were going through that, and we got to the monotonicity formula, which Shane and Ullenbeck proved that for minimizing harmonic maps. And Leon said, I wonder why they didn't do it for stationary, because you can do it for stationary in the minimal surfaces case. And I asked Leon, well, how do you prove it for stationary? And he said, well, you come up with an explicit variation. I think he probably said that it was sort of like a local expanding thing. I've forgotten what he said after that. Anyway, I went away and came up with the monotonicity formula for harmonic maps using explicit variation, exactly as Leon had said you should be able to do. And then I also did it for Yang-Mills. And then I spent a lot of time trying to do the epsilon regularity part that we went through as step 2 in the Shane-Ullenbeck proof. And as I said as comments during the Shane-Ullenbeck proof discussions, I said, I thought the step 3, the extending the regularity for harmonic maps from n-2 to n-3. I said I thought that should go through pretty similarly for the Young-Lewis case. Anyway, and then I stopped. And more recently, I've realized that the blowing up technique, or so the explicit variation I use for monotonicity forming, are pretty much the same, very similar in style, philosophy, to the variation vector fields I use in this presentation, in the second talk of this presentation, to prove some of the vanishing theorem. So, well, that's quite remarkable, or else, it's interesting that the only thing you can do is the only variational vector fields you can do.
Sounds like it was an interesting time to be doing some PDEs.
Yeah, and the theorem I was trying to prove, there were partial results by Terry Tower and Gang Tian, or what I think are partial results, in 2002, and also by Mayer, Yves Mayer and Riviere. And then Riviere and his PhD student Petrarch have announced the n-5 regularity theorem, but it hasn't appeared in full. It's been announced for a long time as in preparation. So, yeah. I said some of that before.
Mm-hmm. Bears repeating, I think. Does anyone have any other questions for Peter?
So the result you mentioned on the homology spheres with positive curvature operator, of course, has been superseded now by the Bowman-Wilking result, which says it's actually a diffeomorphism sphere, up to quotients or something.
Just say a bit louder for me, please, Ben.
Sorry, yeah, I might just turn. The homology sphere result has now been upgraded to diffeomorphism result using Ricci flow.
Right.
I'm wondering whether actually some of the techniques you've talked about might make sense still for Ricci flow and mean curvature flow, at least in the setting of self-similar solutions, because they also become a variational problem. For example, mean curvature flow, the self-similar solutions are sort of minimal with respect to a Gaussian area functional.
Yeah.
Okay. Yeah. So some of these results might go through in those settings, perhaps.
I didn't know about the self-similar flows, but there wasn't much done on flows. No,
right.
There was the initial Ricci flow paper by Hamilton, and I worked on that in 1984, as did Gerhardt, and then I left maths. But I was not involved in flows, but whenever I've sat in on there's been many flows talks as seminars at ANU, and I often, when I sit on those talks, I think, there's equal similarities between these flow work.
Yeah.
Whether it's harmonic map flow, or by tension vector field, or mean curvature flow for minimal surfaces, or Ricci flow, as you say, you can write Ricci flow as an order Lagrange for a variational problem.
Yeah.
You can probably have a Seiberg-Witten flow.
Sure. Yeah.
Yang-Mills flow by what I called the quark density. So, I'd be pretty sure that there's a lot of similarities between all these flow methods and results.
Yeah.
And I guess people know that, is that right?
Yeah, sure. I think that's exploited quite a lot. But this specific sort of framework you've got here with the sort of vanishing theorems may apply reasonably directly, I suspect, in some of those settings. Yeah.
I actually I caught up with Leon Simon around 2010 by phone, when hadn't seen him for decades, when he was at the Isaac Newton Institute. Had a few words about old times in the 79, 80, etc. 81. I said, has anyone come up with a uniform way of treating all these geometric variational problems where this similarity between techniques becomes, examples of using a specific technique? And he actually said, No, doesn't think so. He said we thought that was your job, Peter, but because I was enthusiastic about it. But
Yeah, I think
Okay.
that's right.
so much for that. Yeah. So anyway, interesting stuff.
Yeah. Thanks, Peter. Very interesting.
All right, thanks all. Let's leave it there and let's thank Peter again for a lovely discussion.
Okay, I hope to see most of you in Monday week, I think. Is that right?
Yes, yes. Since hopefully we should encourage everyone to attend the joint Austin S meeting in Auckland next week. We probably should not schedule anything for next week, but our intention is to have the next talk the following Monday. Hopefully not too close to Christmas, but then yes, we'll leave it alone for the year and we'll wish you all a Merry Christmas. But yes, hopefully I'll see some of you at Austin S next week, and if not, hopefully we'll see you Monday the 16th. I think that is correct, and we'll send another announcement out, of course. All right, thanks everyone. I'll stop recording there.